In the nature, there are four fundamental forces, you can say basic forces. All other forces are originated from these four type of forces, and they are gravitational forces, which is very small, but it's noticeable if the mass is big. Another one we will learn later down this course, electromagnetic, and is you see very common, repulsive and attractive. And then the other two, we probably don't get time to study them. Of course, you will, are the nuclear forces, the weak nuclear forces and strong nuclear forces. So we pretty much deal with the first two type of forces, gravity and electromagnetic. Having said that, there are only four fundamental forces, but here realistically we see all kind of forces. Don't confuse the concept that we talk about different type of forces, different situation forces are applied. All right, so realistically there are many type of forces that they are originated from these four type of forces. So once again, most commonly is gravitational force, actually is called the weight. And spring force, if you have a spring, anything that elastic, and you stretch something and push something, when any material, when it is deformed, when it changes shape, there's always tendency to restore back to its original shape. That is called basically the spring force. The spring force will follow Hooke's law. Later you will understand. And also tension force, and along a string. You stretch a string or rope or any thread, and it will have. And tension force, for example, is also it is like a spring force in nature. And also normal force, the supporting force. If you put something on top of a surface and the two surfaces touches, then there will be interaction between the forces that are perpendicular to the surface or the interface. In fact, it is a spring force in nature. For example, you're standing on a table, and the table yields a little bit down, and then there's actually kind of like a spring. Another type, and also is interaction between friction forces, rubbing due to the roughness. Then friction forces are also between two surfaces, interfaces, but they are along the interface, which means parallel to the interface. We will deal with this, we will solve many problems with the friction force. Another type of force, and also it's spring force in nature, and it's called a drag force, resistance force in the fluid or air. So, and these type of forces are seem very common and in the opposite direction of the movement, or the opposite direction of the velocity. Now then we will have some exercises to deal with all these different type of forces one by one. Now let's solve a few problems dealing with the gravitational force between two objects. Newton discovered that there is attraction force between any two objects and in the universe, and the attraction force is along the line between the two objects, and they are proportional to the mass product of these two, and it is the force become weaker. Okay, it follows sort of the inverse square law, which means if the distance is twice as far and the force is 4 times weaker, and is followed by this formula. So a product of mass, okay, so more mass, more attraction, and the farther the distance and the weaker the force. And overall in daily life this is very small. That is reflected in this gravitational constant at g. When g is a very small number, and you will find the exact value of g in any of the physics textbook is like 10 to the negative 11. So if you have any two objects, although they are attractive force between any two, for example, the table and the chair, your pencil and your eraser. But if you put in the mass, whenever you multiply with the g, that is very small. It's not noticeable. Okay, but what if the one of the mass is huge, like Earth, and then you have your object, and then if you do this calculation, you will have some sensible or significant force, so which means noticeable. Now let's take a look at our first exercise. Find the magnitude of the gravitational force between a planet, which it has a big mass, and it's known where the mass smaller but still huge, 2.7 times 10 to the negative 22, but notice 10 to the negative 22 and 24. It's about 2 orders of magnitude smaller, but 100 smaller, but both of them are huge, therefore there are attractive force between them. If the average distance, of course, is big, 2.8 times 10 to the 8 meters, that's like a billion miles, so a million miles away. Okay, and then find the magnitude of the force. So basically we're doing calculation. All right. So A, we are asked to find out what's the magnitude of the force. And so we have to have all these numbers. So G, if you look it up, it's, as I said, it's a very small number. It's 6.07 times 10 to the negative 11. So it's meters cubed, kilograms to the negative 1. So all these, and seconds to the negative 2. So these are all be cancelled later on. Okay, and then the mass. So the mass of the planet, so I will call it mass 1. It's the larger object. It's 7.5 times 10 to the 24 kg. And the second object, mass 2, is 2.7 times 10 to the negative 22 kg. Is smaller. So, and the distance between the two, which is called r, like a radius, is 10 to the 8 meters. Is a large distance compared to our daily life distances. Okay, meters, 10 to the 8 meters. So basically I copied down the data. So what will be the force? So the force is G, so G 1007 So if we just plug all these numbers into the formula, just drop the units. If we do the math, and the force, the magnitude of the force will be 1.7 times 10 to 20 newtons. That's a large force. So that's A. So B. Now I have another exercise, 7.5.33. An International Space Station has a mass of 4.9 times 10 to the 5th. It's like 40 tons in that many kilograms. And the orbits around the radius of 6.7 to the 6 meters. Usually, just to give you an idea, actually compared to the size of the Earth, the orbit of the space planet basically is on the surface of the Earth. Compared, it's like several kilometers above. So from the center of the Earth, okay, so that's a distance. Find the gravitational force exerted on the Earth. So that's exactly apply this formula. I mean, you apply this. Therefore, you have mass of the Earth, and you can find out the book, which is very heavy, 10 to the 24 kg, and mass of space station, which I got from here. And again, gravitational constant is a very small number, but the mass is big, so that we can have some significant number and the distance between the two objects. So you plug in this formula and you will get, of course, you go through the math instead of using the video time. So 361 times newtons. How strong that force is? Because it's a heavy, 40 tons. It will be like 100 newtons. 40 tons is like 400 newtons, but of that. But then, so it's much weaker already. So for the object. Now, let's look at the second question. The weight of the 80 kilogram astronaut living inside the space station. Now we ignore the B for time being because we haven't talked about the energy yet. We work on the C, the weight. Okay, I keep on saying the weight and mass are different. The weight is nothing but the gravitational force. So since the astronauts is already away from the Earth, so the force, the gravitational force is weaker. Therefore, the weight is weaker. So now let's go through the mass. Let's go through that. Let me get my pen. So C, and the gravitational force, again the same formula. So I simplify the mass a little bit. 6.67, that's from G, and so 5.97, that's from the Earth's mass, and now 8.0, that's the astronauts' weights, and divide by 6.79 and squared. So that's the distance between the Earth center and the astronauts. And then I think you just review your math. You can work on the exponents all together later. So you cancel the exponents, then you 10 to the negative 1. Okay. So now, then that work out the math and you will need to work out it. It's like 0.69 newtons. Very small. Okay, I would say small. Smaller than what it's, but the Earth does attract him, but with much smaller force because the acceleration, because it's away from it and it's very small. So if it were on Earth, you will have this 80 times 9.8 is around almost 400 newtons. But on the space station, the astronauts is much weaker, only about less than 1 newton. So if you envision the picture, it goes like this. So it's on Earth. If he's on Earth, so they will have 400 newtons on him. But if you're away from Earth on the space station, okay, like we did in the lab, it's a very small force, is only 0.69 newtons. So that's 400 versus 0.9. So the farther away and the weaker the force. So that's gravity. As we started the class, this 7.735, a coordinate system is constructed on the surface on the pool table. There are 3 objects, and there are 3 objects. One at the origin is 2 kilogram, and another one at 3, and another one at 40. So they both exert a gravitational attractive force on 2. So, and then on 3. We are asked to find the resultant force, which is probably in this direction. Okay, and now we find the magnitude of both of them separately, and then do the vector addition and find the resultant force. Now, 3 on 2 is in upward direction, but numerically the magnitude is 3 times 2 kilogram divided by distance squared and multiply gravitational constant g. But that part will easily work out at 1.5, but we leave the g alone because it's a very small number, and we will deal that with later. We just think about this g as if it was a unit. Well, g4 on 2 is the same idea. The mass of the two, distance squared, g. We leave this complex here as if it was the same. And now, let me write down some more. So the magnitude of these two is this. Magnitude resultant, I will leave the units alone, so magnitude, and it's 1.5 squared plus 0.5 squared, and you do the math, it end up with actually 1.58, and with the same units. Now I can find the magnitude by square of these two, okay, and like the Pythagorean law, because they are perpendicular to each other, and it's 1.5 times that units. So that's in that direction. So the resultant is in this diagonal direction, and then of course actual angle you have to go arctangent y direction versus 1.5 versus 1.5, which is actually 3. And you do that, it actually is 71, okay, instead of 75, and that's angle. Now, the actual value is actually 1.58, but times these units. Now we take care of the g, which is a very small number. 1.58 times g, which is 6.67 times 10 to the negative 11, is actually end up with, I have here as 1.05 times 10 to the negative 10 newtons. It's a very small number. Yeah, this problem also shows you a math trick. Okay, you don't have to carry this small number around and until the last moment, just expand it. So that's this many newtons, and the direction is in this direction. So in fact, that is actually force is in this direction finally. So it's 71 degrees relative to x-axis. Hope this is helpful. If you have questions, we can always talk about separately. Now we are on spring force. Spring force to a limitation and follow the Hooke's law, which means the stronger the extension, the stronger the restoring force. And the restoring force is in the opposite direction of extension, which means restoring the extension. And then, of course, the strength or the stiffness of the is described by this constant called a spring constant, or you can think about the proportion constant when it's linear. So, and we have discussed some conceptual questions in exercise 2. Now here we are solving problems dealing with the Hooke's law. So suppose the x direction is the positive direction. A spring has a spring constant K equals 5 Newton per centimeter. In other words, if you stretch the string 1 centimeter, its restoring force is 5 newtons, or outwards. If you compress 1 centimeter, and it will push outward, and then say 5 newtons, and the relaxed length of the spring is 12 centimeters. Now find A, the magnitude and the direction of its restoring force if it is compressed to 10 centimeters. So in A, so delta x
and the change is always equal to final position versus initial position. The initial position is 12, final position is 10, it's compressed. Therefore, the displacement or the extension is -2. Now, you simply use the formula of Hooke's law. The force is -k and 5 Newton per centimeter times -2 centimeter, and then you will get 10 newtons. In other words, if you compressed, the restoring force is 10 newtons to the x direction. Therefore, it's positive. Okay, B. The magnitude and direction of the restoring force if it is stretched to 17. So in this case, it was 12 and stretched to 17. And then again, you use the same definition of the extension. Final position, now it's 17 minus 12. And then this time it's 5 centimeters. So it's stretched. And of course, down here, hope we can see. Then that's -k is 5 times 5 centimeter, and then next time is a -25 newtons. What does that mean? It goes negative, which means if you stretch it, the spring is going to go backwards. Okay, and stretch it to 17 and go backwards to its original position. So therefore, it is -25 newtons. The third question is combine the spring's properties with Newton's second law. If a weight of 5 kilograms is attached to the end of the spring and released after the spring is attached to the same position, 17, what is weight's acceleration? So there's a force, restoring force on the weight. So what will be the acceleration? Then that's simply Newton's second law again. Force and divided by the mass, and it will give you an acceleration. So force is -25 newtons, because the spring is stretched, so it tries to shrink back, so it's -25 newtons, and 5 kilograms, that's the weight, and pull back, so the acceleration will be 5 meters per second squared. So that's this problem.